Welcome to the first part of lecture 2 in bmb540. In this lecture, in lecture 2, we will study enthalpies of chemical change, enthalpies of physical change, phase transitions, and I will introduce to you the second law of thermodynamics and entropy. We will cover the first three topics in this video. Before I do all that, I would like to show you a video, an animation of a molecular simulation where DNA is being pulled through a bacterial toxin sitting in a membrane. Let us see, there it is. So what you see here is a lipid membrane, and inside a lipid membrane is a bacterial toxin shown in light blue, and this bacterial toxin has a hole in the middle. And here what is being done is an electrical potential is being applied across the membrane to pull the DNA through. Because DNA is negatively charged, it will respond to an electrical potential. The DNA is shown in orange. And this is a molecular simulation, a molecular dynamics simulation. You will encounter this in one of your laboratories. Oops. So here it is. The DNA is being pulled through the toxin. And you can see that at a certain point, the speed at which it is being pulled increases. Let's play that again. An electrical potential is pulling the DNA through the toxin. It is slow now. And now suddenly the speed of pulling increases. We will come back to this video in the second part of the lecture. A quick recap. In the previous first 5 lectures, or the first 5 parts of lecture 1, we looked at the ideal gas law, pressure times volume equal number of moles multiplied by the gas constant multiplied by the temperature for an ideal gas. We then looked at the first law of thermodynamics, which states that the internal energy of an isolated system remains constant, or if the system is not isolated, the change in internal energy is equal to the sum of the heat flow and the work flow into the system. This work can be of several different types. And then we had a video which talked about only mechanical work, which can be calculated from integrating minus pressure times the change in volume. For a constant external pressure, it is given by this term. So this was the measurement of mechanical work W here. And then you can also measure heat. And this is typically done in a calorimeter. And we define the heat capacities. So the heat capacity at constant volume is the change in internal energy divided by the differential change in temperature at constant volume. Similarly, you have a term for the heat capacity at constant pressure, which states that Cp equals dH by dt, where H is the enthalpy. Enthalpy is a heat transferred at constant pressure. So this is probably one of the new terms you have heard of. And we need it because we do need to define heat transferred at constant pressure, because most of the processes we will be looking at will be performed at constant pressure. Note, when the change in temperature is 0, for ideal systems, the change in internal energy and the change in enthalpy must also be 0. The definition of enthalpy is the internal energy plus the product of pressure times volume. CPM and CVM are the molar heat capacities at constant pressure and constant volume, and this is the relationship between them. Good. A few more terms that we should define. Some processes, an isothermal process is a process occurring at constant temperature. An isobaric process is a process occurring at constant pressure. We have not talked a lot about adiabatic processes, but most of the biological reactions that occur in cells are adiabatic because the process is very fast and there is no time for heat transfer. An adiabatic process is one where there is no heat transfer. We also talked about reversible and irreversible processes in the previous lecture. Reversible processes are slow and the work done is higher than in irreversible processes. We also defined state functions, functions which do not depend on the path, and these are internal energy and enthalpy. Heat and work are not state functions because they depend on how you go from state point 1 to state point 2. Enthalpy for us is a number that we use for bookkeeping, for tracing the flow of energy in most processes that we are concerned with, which occur at constant pressure. So chemical or biochemical reactions in the cells are mostly occurring at constant pressure. There are enthalpies of chemical change and enthalpies of physical change. Enthalpies of chemical change refer to changes where new chemical species are being formed or old chemical species are being destroyed. A simple example is an exothermic process which releases heat, for which by definition the change in enthalpy is less than zero. And an example is the burning of glucose or the metabolism of glucose. A single molecule of glucose gets metabolized by 6 molecules of oxygen and releases carbon dioxide, water, and there is something missing in this equation, which is energy. Oxidation of any fuel is an exothermic process. There are very few examples of endothermic processes where the change in enthalpy is greater than zero, and we will not talk about these very much. Before we go further and talk about enthalpies of physical change, we must understand what are standard enthalpies. And before we do that, we must understand what is a standard state. The standard state of a substance is its pure form at exactly 1 bar. So the standard state is either solid, liquid, or gas. For example, the standard state for ethanol at 300 Kelvin is liquid ethanol at 1 bar. It is not um, solid ethanol or gaseous ethanol. So let us look at the standard enthalpy change for this physical reaction here, where liquid water is being frozen to, liquid water is being vaporized to steam or vapor. The standard enthalpy change is signified by this symbol here on top of H. refers to a vaporization process, and the standard vaporization enthalpy of water at 373 Kelvin is given by 40.66 kilojoules per mole, which means that the amount of enthalpy which will be released or will be absorbed when you heat 1 mole of water from liquid to gas at 100 degrees centigrade is about 40.66 kilojoules. This reaction absorbs energy because you need energy to heat liquid to gas. Another example is melting of ice into water, and this is given by delta H melt. The standard sign is missing here. And the liquid to solid transition is called fusion, FUS. Similarly, the solid to gas transition is called sublimation. So these are standard enthalpy changes of phase transitions. Um, since you are biochemists and molecular biologists and those studying biomedicine, we will not talk a lot about enthalpies of chemical change, um, but we will talk a little bit more about phases. So this transition here is from the solid phase to the liquid phase when ice is melting. So let us try to define what a phase is. At the bottom of the slide, you can find the definition of a phase, and this you should remember word by word. Phase is a form of matter that is uniform throughout in both chemical composition and physical state. For example, ice is a phase, liquid water is also a phase. A phase transition occurs when one phase changes into another spontaneously at a given temperature, such as melting, vaporization, or sublimation. So here, if this animation shows an ideal gas, which has two types of ideal gases colliding against each other. It's an ideal gas mixture. This is a single phase because on an average throughout the chemical composition is the same. So for example, this might contain 10% red and 90% blue. And the physical state is also the same. So the system has a given pressure and temperature that does not change. Ice is a single phase, again, something that is uniform in chemical composition and water, no matter which part you make the measurement in. A slurry of ice in water, on the other hand, is two phases. There is a liquid phase and a solid phase. Here is a solution, a pictorial description of a solution of salt. So if you take some salt and you take some water and you dissolve it, all the sodium and chloride ions are eventually surrounded by water. So this is a hydrated sodium ion and this is a hydrated chloride anion. And the question is, if a phase is a form of matter that is uniform throughout in chemical composition and physical state, then how many phases does a zero point 0.5 molar solution of sodium chloride have? Does it have one phase, two phases, or three phases? And the answer is it is a single phase, because anywhere in this solution, if you measure the composition, it will be equal to 0.5 molar. And anywhere in this solution, you will have the same physical liquid state. Here is another example, a lipid vesicle, which consists of a lipid bilayer which closes upon itself. There is water inside, there is a lipid bilayer outside, and the question is, how many phases does a lipid vesicle have? Does it have 1, 2, 3, 4, or 0 phases? And the answer is it has two phases. One phase is the lipid bilayer phase, and the other phase is the water inside. All the water inside, except the one at the boundary here at the interface, has the same chemical composition and the same physical state, macroscopically measured, and the same is true for the membrane. So this was a simple lipid vesicle containing one lipid. Here is an image of a cell membrane which contains several different types of lipid, maybe up to 1,000 different lipid species, and cholesterol, and a lot of proteins, which are either integral membrane proteins shown here, or a peripheral membrane protein shown here, maybe an ion channel, and it also contains glycoproteins. It also contains actin filaments just below the membrane. The question is, how many phases does a lipid membrane have? And the answer is, it is unresolved. So lipid membranes, which have complex chemical compositions, can separate into different phases. For example, they can form what is called a lipid domain or a raft, where certain types of lipid come together, such as phingolipids and cholesterol, and form a region which has a different physical property. It can be more ordered than the rest of the membrane. A phase transition is the spontaneous conversion of one phase into another and occurs at a characteristic phase transition temperature. For example, ice at 1 atmosphere will always melt at 273 Kelvin. Water at 1 atmosphere will always boil at 373 Kelvin. Interesting things happen to the enthalpy and the heat capacity at a phase transition. Let us look at a simple phase transition for, let's say, a pure liquid. On the y-axis here, on the left-hand side, we are plotting volume against temperature. For most substances, let's assume this is not water, but for most other substances, the temperature, as you increase the temperature, the volume increases. So this is the liquid, the volume is increasing. At the phase transition, the temperature doesn't change, but As liquid becomes gas, 1 mole of a gas occupies a much larger volume than 1 mole of a liquid, and the volume suddenly increases, and it keeps increasing as the temperature increases. Enthalpy, if you look at this equation here, enthalpy is given by the heat capacity multiplied by the change in temperature, and the enthalpy increases with temperature. At the phase transition, the enthalpy of the pure substance in the two different phases is different, because also the heat capacity is different, and therefore the enthalpy spikes all of a sudden at the phase transition temperature shown here by the dotted line, and then keeps increasing as you increase the temperature. If you plot the heat capacity versus temperature at the phase transition, as you can see, the change in enthalpy is very high without a change in temperature. So dt is very low while dH is very high, and therefore the heat capacity spikes, or is a delta function in the ideal case, at the phase transition temperature. What is actually happening is, as you increase the temperature, the kinetic energy away from the phase transition temperature, the kinetic energy of the system keeps increasing. The potential energy also increases, but the kinetic energy directly depends on the temperature and keeps increasing, which is why the enthalpy also increases. At the phase transition temperature, if you're looking at ice, for example, there are strong hydrogen bonds between different molecules of water in ice. As you increase the temperature, the kinetic energy of these water molecules keeps increasing until you reach the phase transition temperature, where the kinetic energy of individual water molecules is high enough that they break the lattice of ice, and then water is formed, which also has hydrogen bonds between water molecules, but these are much weaker than they are in ice. What about phase transition for biological systems? So here we have a lipid bilayer, which, as you all know, is formed of lipids. Um, a lipid membrane has two hydrophilic interfaces, which sandwich between them a hydrophobic region. If you take a lipid bilayer at a very low temperature, it will be in what is called a solid or a gel phase, where these lipid tails are aligned to each other. As you increase the temperature, the kinetic energy of these lipids increases until there is a small phase transition temperature, leading to the formation of what is called the ripple phase, which has this characteristic shape. If you increase the phase transition, if you increase the temperature further, you get another phase transition, after which the membrane becomes fluid. So here on the left hand side, we have a gel-like lipid phase. On the right hand side, you have a fluid-like lipid phase. On the right hand side are simulation snapshots of what a gel-like phase looks like and what a fluid-like phase looks like. In the fluid phase, the lipid tails are very disordered. In the gel phase, the lipid tails are highly ordered. And in this plot, of course, we are plotting the heat capacity versus temperature. Page 264 in your textbook Korean contains an excellent discussion of the phase transition of the unfolding of a protein at low temperatures, and I strongly recommend that you read these pages. It also contains a very good discussion of the phase transition of the unfolding or the melting of DNA. At point A, all the protein is folded. As you increase the temperature, the kinetic energy of individual atoms increases. At As you approach the phase transition temperature, you can see that the heat capacity increases, because even though you are increasing temperature, even though you're supplying heat to the system, the temperature does not increase, because most of the energy you're supplying to the system is not increasing the kinetic energy, but is being spent in increasing the potential energy in the system, where hydrogen bonds and, for example, salt bridges are breaking. Note that the phase transition is not as it would be in a pure gas like here. The heat capacity is not very high, but is almost Gaussian, and this is because all the proteins do not start unfolding at the same point. At point B, a minor fraction of the protein is unfolded. At point C, half the protein is unfolded. As you approach point D, most of the protein is unfolded. and at point E, all of the protein is unfolded. And then when you supply more heat to the protein, the kinetic energy, most of the heat is spent into increasing the kinetic energy of the molecules, and that increases the temperature. In your first computational laboratory, you will calculate the heat capacity of a phase transition for an alpha helical peptide. Normally, such a curve, like the one shown for the lipids and like the one shown for the protein, is obtained using a differential scanning calorimeter. You can read more about it in either of your textbooks. So, this was the first part of lecture 2. In the second part, we will start talking about the second law of thermodynamics.